This is the harmonic oscillator. It's primarily about the harmonic oscillator, but a few notes first. Stationary states can take the form of linear combinations given here, and uncertainty, there's which the word uncertainty gets thrown around a lot in quantum mechanics in regards to position and momentum. Well, in any case, the uncertainty principle, Heisenberg uncertainty principle, in any system, in any state, the uncertainties of position and momentum obey this inequality, which is h bar over 2. This inequality involves position and momentum along some axes. Similar is also applied to uncertainty products amongst y and position of y and change of z and position of z, but x and change with y wouldn't make any sense because it involves position and momentum of different axes, so it does not obey the inequality and can in principle be equal to 0. Now let's start with the oscillators. A classical harmonic oscillator. Consider a particle of mass m that moves to and fro along the x-axis with a position of stable equilibrium at the origin of x equals 0. When the particle moves away from the origin, it feels a force pulling it back towards the origin. In simple harmonic motion, this form is proportional to the displacement f of x equals minus c of x, where c where this is Hooke's law and c is a force constant and x is the displacement from equilibrium position at x equals 0. The minus sign means f of x is a restoring force. It pulls the particle back towards equilibrium. In classical physics, motion is governed by Newton's second law, which I'm assuming everyone's familiar with, which is mass multiplied by acceleration. Which can be rearranged to give this form here, where omega 0 is square root of c over m, which is constant, which is the angular frequency, I believe. Omega is often referred to as such. The equation xt of a cosine omega t plus phi is the sinusoidal motion, and the graph would oscillate above and below the x-axis. In this model, unrealistically, there is no damping, so it's effectively perpetual motion, which is nonsense in the real world. As always, a is amplitude and phi is the phase and omega is the angular frequency. Now, simple harmonic motion can be analysed in terms of energy. The potential energy of a simple harmonic oscillator is V of x is 1/2 cx squared, which is the as a minimum V equals 0, and the equilibrium is x equals 0. Now the particle has momentum P of x m V sub x, and kinetic energy E kin, which equals 1/2 mv mv squared x equals the momentum operator of x squared over 2m. Adding these combinations gives the total energy E equals px squared over 2m plus 1/2 cx squared. Now let's consider a diatomic molecule in classical physics, where we have two masses, mass 1 and mass 2. Several types of motion are possible: translational motion as a whole, rotational motion, motion around an axis, vibrational, the bond between them. In carbon, we have two particles. In CO, we have two particles, carbon and oxygen. Which interact rather than a single particle responding to an external force. Ignoring external force and rotational motion and placing x-axis along the line of action gives the total energy of the particle as such, whose first term is kinetic energy of an atom, and of atom 1 and the second is of atom 2. The last term is the potential energy and the interaction between the two atoms, which depends only on distance. Now, changing the variables can simplify this equation. We have E equals p squared over 2m plus p squared over 2m plus v sub x, where m equals mass 1 plus mass 2, and the uppercase P equals P1 plus P2, and these are total mass and momentum of the molecule, and the other variable x is x2 minus x1, and mu is mass 1 mass 2 mass 1 multiplied by mu 2 mass 2, sorry, mass 1 multiplied by mass 2 divided by mass 1 plus mass 2. And P equals mu dv by dt, which is the acceleration, which now p squared over 2m is translational motion of the whole system. This term has nothing to do with any internal vibration and can be set to 0 by agreeing to work in the center of mass reference frame. In the center of mass reference frame we have this, which is just like the energy of a single particle, with its potential energy provided by a fixed external agency. The mass mu equals mass 1 multiplied by mass 2 divided by mass 1 plus mass 2 is less than either m1 or m2, and is called the reduced mass of the molecule. And that's harmonic oscillators.